In this lesson, we are going to derive 7 more properties using the first 3 properties of determinants. The fourth property says that if A has 2 equal rows, then the determinant of A is equal to 0. This can be proved using the second property of determinants. Specifically, suppose that you swap 2 rows of A. That changes the sign of the determinant, as the second property tells us. Now let's suppose that you actually swap the equal rows. If you do that, then the determinant of A is equal to negative the determinant of A. The reason is because you swapped rows, so you have to take the negative sign of the determinant, but you swapped the equal rows, so the matrix did not change, so you still have the determinant of A. This, by default, leads us to one conclusion, that the determinant of A is equal to 0. The fifth property says that the elementary row operation of adding L copies of row I to row J leaves the determinant unchanged. So let's take an original matrix ABCD and let's add L copies of the first row to the second row. Then the determinant becomes the determinant of ABCD plus the determinant of AB, LA, LB. What we did here is we used the third property where we split apart sums. So we split apart the second row of the original determinant into CD, we kept the first row unchanged, and into LA, LB, keeping the first row unchanged. Now we are going to use the third property of determinants again by pulling out constants here. This gives L times the determinant of AB, AB. But here 2 rows are equal, and we just proved that if 2 rows of a matrix are equal, then the determinant must be 0. So we end up with the determinant ABCD. In other words, adding a copy of one row to another row leaves the determinant as the original determinant, which is just ABCD. The sixth property tells us that if the matrix A has a row of zeros, then the determinant of A must be 0. Let's consider the following 2 by 2 example. Say that the first row of A is 0, 0, and the second row is CD, where C and D are non-zero. And let's say we are computing the determinant of this matrix. Then what we can do is write the first row as follows. Here I wrote the first row as 0 times some constant A and 0 times some constant B. So we did not in fact change anything about the first row. But what I can do here is I can pull out a constant now by using the third property. So what I'm going to do is pull out the 0 from the first row, and here is what I get. So now I have 0 times the determinant of ABCD, which is simply just 0. The seventh property tells us that if A is a triangular matrix, whether upper triangular or lower triangular, then we can compute the determinant by taking the product of all of the diagonal entries. Consider, for example, computing the determinant of the following upper triangular matrix. Here I'm going to make the assumption that these diagonal entries are non-zero. The reason I do that is because now I want to take each of these entries, which are in fact the pivots of this n by n matrix, and use these pivots to eliminate all of these entries right here. This will give me a diagonal matrix which has all of the original pivots of the matrix A. As we know from the third property of determinants, we can now pull out constants from each row. For example, the first row we can pull out A11, from the second row we can pull out A22, from the third row we can pull out A33, and so on, until we get the following. Now we have a product of A11, A22, and all of the other diagonal entries multiplying the determinant of an identity matrix. But we already know from the first property of determinants that an identity matrix has a determinant equals to 1. So this gives us the product of A11, A22, all the way up to ANN, or in fact, the product of the diagonal entries. And this proves the seventh property. The eighth property tells us that a matrix A is invertible if and only if its determinant is not equal to 0. This property, in fact, follows directly from property number 7. Now notice that if the determinant of A had been 0, then there must be a 0 pivot. But if there is a 0 pivot, then we have less than n pivot for an n by n matrix. And as we know, if there is less than n pivots in an n by n matrix, the matrix is not invertible. The ninth property says that if we multiply two matrices together, A and B, then the determinant of A times B is simply the determinant of A multiplied by the determinant of B. We are not going to prove this property. However, what I'm going to do is show you how you would do it for a 2 by 2 example. Let's say you have two matrices, A and B, which have entries A, B, C, D and E, F, G, H. Now let us compute the determinant of A. The way we are going to find this number right here is by using the properties that we have already derived. The first thing that I'm going to remember is that there is a property which tells me that if I add a copy of some row to another row, the determinant remains unchanged. So here's what I'm going to do. Let's call the first row of this determinant R1 and let's call the second row R2. Now what I'm going to do is use the first row in order to get rid of this C right here. So I'm going to subtract C over A copies of the first row from the second row. Or in other words, I'm going to consider R2 minus C over A copies of R1. Now this is going to give me the following result. And notice that I am equating this determinant to this determinant, because in fact all I did here is use property number 5, where I added some copies of the first row to the second row and I obtained this new second row, and that leaves the determinant unchanged if you go back to property number 5. Now we are going to use the property that tells us that the determinant of an upper triangular or lower triangular matrix is simply the product of the diagonal entries. So here we have the determinant of an upper triangular matrix, so all I'm going to do is multiply the diagonal entries. So we get A times D minus C over A times B, and this gives us AD minus CB. If you want a way to remember this, the way you do it is you multiply the diagonal entries A times D, and you subtract the product of the off-diagonal entries C times B. Using this observation, we can say that the determinant of B is simply E times H minus F times G. Now, as I said, I am not going to really prove this property, but here's how you can continue. What you could do is you could multiply A times B and get an expression for A times B. Then you could compute the determinant of A times B, and then compare it to the determinant of A multiplied by the determinant of B from the determinants we just computed above. The 10th and last property that we are going to derive today is that the determinant of A transpose is equal to the determinant of A. We are going to consider two different scenarios. The first scenario is if the determinant of A is equal to 0, and the second scenario is if the determinant of A is not equal to 0. Now, in the first case, we know that the row echelon form of A is going to have a 0 pivot. This by default means that the row echelon form of A transpose is also going to have a 0 pivot. But we know that if the matrix has a 0 pivot, then its determinant must be 0. So the determinant of A transpose is 0 and is equal to the determinant of A. Now let's consider the second case when the determinant of A is not equal to 0. In this case, we know that A is not singular, meaning A is invertible, which means that the LU decomposition of A exists. So writing P times A equals to L times U, we can compute the determinant of PA and set it equal to the determinant of LU. Now, using the product of determinants, this determinant is going to be equal to the determinant of P times the determinant of A is equal to the determinant of L times the determinant of U. I can also take this formula and take the transpose on both sides so that I can write P times A transpose is equal to L times U transpose. Now the left-hand side is going to give us A transpose times P transpose, and the right-hand side is going to give U transpose times L transpose. Next, I'm going to take the determinants on both sides. So we get the determinant of A transpose times the determinant of P transpose is equal to the determinant of U transpose times the determinant of L transpose. Notice that U is an upper triangular matrix and its determinant is going to be the product of its diagonal entries. Now U transpose has the same diagonal entries as U and it is a lower triangular matrix, so its determinant is also going to be the product of its diagonal entries, and hence the determinant of U transpose is simply going to be equal to the determinant of U. In the same spirit, L is a lower triangular matrix and its determinant is equal to the product of its diagonal entries. Now L transpose is upper triangular matrix with the same diagonal entries as L, which means that the determinant of L transpose is simply equal to the determinant of L. All we have left to do is show that the determinant of P transpose is equal to the determinant of P. This will require a few details. Remember that P inverse, or the inverse matrix of permutation matrix P, is equal to P transpose. And remember that P inverse times the matrix P is equal to the identity matrix, which means that P transpose times P is equal to the identity matrix. Now, if I take determinants on both sides, this tells me that the determinant of P transpose times the determinant of P is equal to the determinant of the identity matrix, which is simply 1, as we saw in the first property of determinants. So this means that the determinant of P transpose is in fact 1 over the determinant of P, and not quite the determinant of P. But there is something that is worth noting here, is that P is a permutation matrix, which means it has the rows of the identity matrix shuffled. And if all you're doing is shuffling rows of the identity matrix, this would mean that the determinant of the permutation matrix is going to be plus or minus 1, which means the determinant of P transpose is also going to be plus or minus 1, which means the determinant of P transpose is actually equal to the determinant of P. Now that we have everything, we have determinant of A transpose times the determinant of P transpose, which is the same as the determinant of P, is equal to the determinant of U times determinant of L. And this is the same expression as that for the determinant of A. So we can conclude that the determinant of A transpose is equal to the determinant of A. Now let's consider computing the determinant of the following matrix. The way I'm going to do it is by writing this matrix in upper triangular form or in row echelon form. So what we're going to do is take the first pivot and use it to remove the 2 entries below it, and then find the second pivot and the third pivot and so on. Adding 1 copy of the first row to the second row gives us the following, and subtracting 3 copies of the first row from the third row gives us the following. Now all we have to do is actually exchange these 2 rows in order to get upper triangular form, and here's the result. Notice that I multiplied by a negative sign, and this is because I swapped 2 rows, and remember, when we swap out rows, we have to change the sign of the determinant. Now that the matrix is in upper triangular form, all we need to do is multiply the diagonal entries to get the determinant. So we have a minus sign that we shouldn't forget, 1 times 5 times negative 2, and the answer is 10. In the last part of this lecture, we are going to talk about some formulas that are used to compute determinants. I'll see you there shortly.